Okay, thank you. So this talk is based on joint work with several people, but I especially want to call out Alexei Radl, who is the lead engineer on Venture for several years, and Ulrich Schechtel, a postdoc in my group. So in this talk, I'm going to try to propose that we should consider a change to the conceptual model of probabilistic programming that we've seen reflected in some of the talks today, and I think that's been most prominent in the PL community. In particular, I'm going to propose that we ought to try to make inference programmable. So I'm going to spend a good chunk of time in this talk really just trying to give you a sense of what the need is for programmable inference or inference metaprogramming. And then I'm going to spend some more time describing what inference metaprogramming is, first by showing you a quick overview of some real-world case studies where using inference metaprogramming we can take complex systems that might be around 4,000 lines of code in a language, in one case like MATLAB, another case like C++, and compress them dramatically. Then I'll go through a tutorial example that'll give you a hands-on sense of what the mechanisms of inference metaprogramming are, and a list of some of the capabilities that inference metaprogramming provides and what's implemented in a prototype system we have called Venture that implements them. And then I'll close with a summary of future research and some of the contributions, and places where we need much more help and engagement from the PL community. So the setting for probabilistic programming is that across many fields, we're seeing probabilistic models and inference algorithms become increasingly prominent. So let me just give a few examples to give a sense of both the centrality and the diversity of these techniques in computing. So we can imagine a typical problem in biomedical statistics is to take multivariate data that characterize patients and outcomes and covariates that might predict outcomes under various treatments. And there's an inference problem, which is to go from that data to estimates of the effect sizes. So we might build a model of the size of the effect of treatment. And the algorithms we might use to do inference in that model are, let's say, Markov chain Monte Carlo to try to quantify the uncertainty very carefully, because maybe there's going to be an expensive decision that's going to be made about a trial design, clinical trial to run. That's one setting. But another setting where probabilistic modeling and inference sees heavy use is in robotics, where we might be trying to track the position of, let's say, an autonomous vehicle and the people in its environment. So we might have a model for those tracks. And the inference algorithms we might use are particle filters, which try to locally follow the uncertainty about the locations of these objects, relying on the fact that from second to second, the locations of everything don't change too quickly. A third case where modeling and inference are used are in machine learning applications, where, for example, we might view the parameters of a neural network as the domain of a probabilistic model. And there, our inference might involve just trying to find a single best setting of the model parameters, maybe using some kind of gradient descent. So these are three different domains with wildly different types of models and also, crucially, wildly different types of inference algorithms. And the differences in the inference algorithm flow from the functional requirements of these applications. They're all pretty different. Okay, now, what's probabilistic programming? Well, the emerging field of probabilistic programming, we're arguing in an upcoming review, is really grounded in two technical ideas. One, that we're going to represent probabilistic models using executable code, specifically code that makes stochastic choices for each latent variable in the model. And we've seen some examples of that. But two, we're going to represent operations on models using metaprograms. Programs that take models as input, or maybe models represented as programs as input, or maybe produce them as output, or both. And these operations definitely include inference. So let's say finding probable values for latent variables, again, like we saw in a talk earlier today. But they also include learning, so finding model parameters and structure given data, querying, making predictions for previously unseen data given a model, and even kinds of analysis or verification, like, for example, quantifying the amount of information between variables in a model. So these are all operations that people normally do a lot of math for in multiple fields, and in probabilistic programming, the proposal is to formalize those as metaprograms. And the goal is to sort of do something that's kind of analogous to what deep learning infrastructure did. This is one framing of the goal. So like systems like TensorFlow and Torch, which factored modeling from inference, but for a broader class of models and operations that go beyond just inference and inference and learning. Okay, but the way that this vision has been realized in most probabilistic programming systems is something like this, where you write a model as code and you put in data and you have a query and then the system somehow gives you an answer. Since working on the first inference engine for Church about 10 years ago now, I've been receiving, I think, quite reasonable critiques of this model. Most of my colleagues in AI and machine learning have said, like, what is this, some kind of magic? There's no way this could possibly work in the generality of the setting that probabilistic programming invites, right? If models can be any executable program and queries are quite unrestricted, then how can you just somehow ignore all the complexity of how to do inference? And frankly, I'm fundamentally sympathetic to that critique of probabilistic programming as presented by this vision. In fact, I stopped working on it after Church for many years because I was so concerned about this as a fundamental limitation. So let's just get a little more texture on that. So again, we've seen many different areas which have different models and different inference algorithms, but even if we just look at statistics, let's say, so you might say, well, what if we restrict the domain to just statistics? Maybe then we can implement this proposal for automatic inference. Well, just in statistics, just in Monte Carlo methods, there are many textbooks on Monte Carlo techniques with many variations of Monte Carlo methods, and the key characteristic of all of them is that for different parts of one problem, you might use very different methods. So I think there's sort of an intuitive argument to be said that we're not likely to be successful if we just try to ignore the inference algorithm as a core object of concern in probabilistic programming. So my sort of key takeaway from this section is there's no one algorithm that can sort of rule them all, and that maybe we should try to formalize the space of inference algorithms and how they act on models. And that's really the departure point for the technical content in this talk. How can we formalize the space of inference algorithms as they act on models? So we're going to introduce this notion of an inference metaprogram, which is going to be a new type of code that interacts with code specifying the model, the query, and the data, and precisely specifies the probabilistic process by which the probabilistic programming system produces answers. And I'll just spend a couple minutes roughly just sketching cases where this has been done in practice, where I think the results are practically interesting, before spending most of the time on a tutorial example that's just very simplified to give you a sense of the nuts and bolts. So one case study we did very early on was inferring 3D models of roadways from cameras mounted on top of a vehicle. So the goal is to basically produce a 3D model of where the road is and where the lane boundaries are from video of a road. I mean, this is a core type of perception problem in robotics. This is one type of case study that you can solve with this kind of machinery. And of course, you can imagine that a key constraint to exploit is that the solution at one frame is pretty close to the solution from the frame before. So that's one case study. Now, here's another case study, automatic modeling of time series data. So here the problem is going from a time series, which maybe, looks, in this case it's atmospheric CO2 levels, sort of rising over time with some oscillations, to a structured description of that time series in terms of a rising trend, a periodic overlay, and some local deviations. So this computation was part of the automated statistician system that made a big splash some years ago. I mean, is one of a larger number of systems for producing automated insights from data. And there are versions of these systems that do work well in practice. They go from data like time series to structured descriptions. And in a problem like this, there's one problem is searching for how to decompose the time series, and the other problem is how to fit the parameters of those decompositions. Those are pretty different problems that might benefit from different inference algorithms. This example is covered in our paper, where it takes about 4,000 lines of code in MATLAB to implement the original automated statistician algorithm, and it takes about 70 lines in Venture using inference metaprogramming. And the inference metaprogram I'm just showing here in a little snippet, what it does is it searches the model structure using a Metropolis-Hastings algorithm, and it adjusts the continuous parameters using a kind of fancy gradient-based search technique called LBFGS that's popular in the literature. And just to be clear, if you use a generic black box inference algorithm like the one from Church on this same problem, given the same runtime, you often get pretty crazy results. So forecasts that just don't match the data. You need the ability to customize the inference to get good performance. A third case study is automatic modeling of multivariate data, like from database tables. And I'm not going to spend too much time on the details here, but this type of system, again, has seen a bunch of real-world use. It involves going from data to models that capture the basic variation in some, maybe moderate dimensional space, like a couple hundred dimensions. Database table with maybe a couple hundred fields, let's say. Here, back-end systems that have seen commercial use are about 4,000 lines of C++, and they correspond to about 50 lines in a language like Venture with a complicated inference metaprogram that's using all sorts of different operations for different parts of the problem. Inferring model structure, adjusting different types of parameters, using different sampling and search algorithms, and even some interesting control flow to determine when you do updates to what variables. Okay, so this is just meant to be a sketch and motivation for sort of the idea that we might need inference metaprogramming and that it's possible to do it in a way that's useful or relevant for real-world problems. Okay, so now let me try to say more clearly or illustrate what it is in a nuts and bolts way. So here's a toy problem where I'm going to interact with a Venture interpreter. And so on the left, I'm showing code, and it's going to come in line by line. And on the right, I'm going to show two things. One, I'm going to show an execution trace of that code, so values of all the stochastic choices made by the code. And I'm also going to show a plot of the true distribution on traces. So if you were to somehow consider all possible executions weighted by their probability. So here I have one line of code that just samples a variable x from some Gaussian distribution. So you can see the full distribution is just some Gaussian. There's a particular value of x labeled. And then the value of x shows up in the trace on the bottom right hand of the slide. And then I can add a y. So now I have x and y. So now I have a Gaussian, which we can see visually. That's the true distribution with a little point on it somewhere for the current trace. And we can see x and y occurring in the trace in the bottom right as well. Now let's say I add in some data. So I observe that a Gaussian whose mean is x plus y and whose standard deviation is 1 is equal to 3. So I've added some data. I've added a constraint. And we can see the distribution shifted. So before it would look like this, sort of this broad distribution, and now it's this narrower distribution that's rotated to the top right. And we can see that there's this new constraint added to the trace, to the representation of the trace as well. Okay. So here I've now defined an inference problem. And in some sense, under the sort of the standard model of probabilistic programming, or what has historically been, what's been viewed as that model anyway, we'd be done. There'd be no more code to write. We'd just feed that into an inference engine and we'd somehow get our answers. Okay. But with inference metaprogramming, we can start to specify instructions that control how the probabilistic programming system explores the space of traces to solve the problem. So for example, I might say do gradient descent, so take gradient steps on a subproblem, which is going to be a subtrace of this whole program, which is generated by grabbing all of the latent variables, the variables tagged with this word latent at once. So that expression question latents is going to create a target set of variables by filtering the variables for their names. You'll notice x and y had these names, latent x and latent y. It's actually a little bit analogous to web programming in a funny way, but you're going to grab those using those labels, you're going to grab them from the trace and then construct a target set, and then from that, construct a subproblem. Or sorry, so if you change those two variables, there's another value, which is, in this case, the constraint from the data that's influenced by those two variables. That's going to absorb changes. That's what an absorbing set is. And together, those comprise a subproblem. In this case, the subproblem is the whole program or trace. I'll show an example later where that's not the case. Once we've got that subproblem, we can apply gradient descent to try to solve it. So I can take one gradient step, which updates x and y simultaneously. And it's hard to see, but the x shifted a little bit. And I can amplify that, so I can do that 10 times. And now I'm just showing the animation of having done that 10 times. You can see the little trace moving. Or I could do that 150 times. You can see the trace moves a lot more, a lot closer to the center of the distribution. All right, so here I've used inference metaprogramming to specify a very simple operation, sort of very standard in sort of the mathematical descriptions of modeling and inference, namely grab some of the variables, find out what they affect, take the gradient of the probability density, and then try to climb it. So that's a common building block of a very broad class of inference algorithms. For deep learning, for example. Now here's another instruction, where now I'm just going to grab the x variable. All right, so here I'm searching for where the value of the tag under latents is equal to x. And I'm going to make a subproblem of that. So if x changes, I still have to consider its influence on the data. And then I can run this resimulation Metropolis Hastings operator, which effectively reruns a fragment of the program that's bounded by that subproblem. And then uses this particular rule that has a nice asymptotic soundness property to decide whether to accept or reject that change. And so it shifted that trace a little bit to the right. And I can repeat that, or I can now do that to y, and now that'll move that little x vertically. Or I can repeat it 100 times, and we can see this little x wiggle around, changing one coordinate at a time. So now I've been making subproblems for single variables, and we've seen these inference metaprogramming operations now sort of wiggle this little trace. And now I can do things like have multiple executions at once. So maybe I'm going to resample 10 copies, reset them to the prior distribution, and then do 150 gradient steps. So we see 10 traces appear and then coalesce towards the center. And then if I do 100 Metropolis Hastings steps on those, we now see a cloud of traces that looks more like a reasonable approximation to the idealized distribution. And I could do this with 100 traces instead of 10. Right? So now we're going to see 100 executions at once. And under the action of gradient descent, they're coalescing towards the higher probability regions. And then if I do some Metropolis Hastings afterwards, we can see them stochastically exploring the idealized distribution and getting a pretty reasonable approximation. So this is just meant to be a simple tutorial example to give you a sense of what it looks like to write custom inference algorithms using a high-level language for inference metaprogramming. And I guess I would claim that skilled practitioners of modeling and inference who know how to use these tools have pictures in their mind that look kind of like the pictures that are being rendered here. And the operations and building blocks by which they can think have some similarity at least to the language constructs that we've introduced in this paper, which are selecting subproblems, figuring out what needs to change if you alter the variables in that subproblem, and then applying different inference tactics to do that. Okay, so just a little bit of a higher level list. In the venture prototype, the inference metaprogramming operations we support are decomposing inference problems into subproblems, applying inference tactics to subproblems, alternating between doing inference given existing data and incorporating new data. So I haven't really illustrated that in this talk, but it's a really important building block for a broad class of sequential algorithms. It's actually very closely related to the incremental inference talk that Marco gave earlier today. And then also exploring multiple traces at once and resampling to focus effort on just the promising traces. And it turns out that this set of operations is enough to span a very broad class of inference algorithms that arise in data science, vision, robotics, machine learning, and a bunch of other fields. As well as generate very new inference algorithms that are too complex to work out the math for to do by hand reliably. The venture prototype also supports an interestingly broad class of inference tactics, that is, for making updates to parts of a trace given a subproblem. And those include baseline techniques like rejection sampling and likelihood weighting, gradient-based optimization, all based on automatic differentiation, Markov chain and sequential Monte Carlo, variational inference, and some advanced MCMC techniques. And there's a tech report online that has the implementation details for many of these tactics. Including how do you maintain the trace data structures and update them efficiently. Okay, so let me just say a couple words about research directions and contributions, and then take some questions. So we've seen maybe, hopefully, that there's a need for inference metaprogramming if we really want to use ideas from programming to raise the level of abstraction at which people do modeling and inference. And I've hopefully also shown you that it's possible. And I've at least asserted that it's possible and even almost practical in some more real-world cases. Okay, but what research needs to be done? So one of them is, in these examples, the metaprogramming primitives, the operations, and the tactics were defined as part of the venture implementation. So there's a clear language opportunity to lift those into user space code to make everything much more configurable. And we've been working on that for a while in a language called metaprob, which we'll hopefully be able to share with you guys soon. Second, and also a language called Gen, which Marco is working on and presented at the Maple conference workshop on Monday. Second, it's interesting to try to define inference metaprograms and tactics that use probabilistic programs themselves to actually define what they're going to do on your subproblem. And so Marco had a paper at the Probabilistic Programming Semantics workshop on that, and there's more research to be done there. Third, performance is a key issue, but it seems likely that some very, very well understood techniques from the PL community could make an enormous difference. So, for example, code generation to generate specialized code for running a tactic on a subproblem seems pretty natural, and that's something we're starting to do a little bit of work on that Marco presented at Maple. And then finally, I think there's an enormous opportunity for visualization, testing, and debugging of inference metaprograms. And this is key because to practitioners in modeling and inference, all of these are only probably approximately correct ways of solving a problem. And the degree of confidence is usually unknown to the practitioner. And so for people who are interested in the soundness questions related to this approach, I encourage you to look at the beginning of the paper that we wrote for PLDI. We tried to sort of frame that a little bit to bridge the gap between the kind of hacking with math world of people who do modeling and inference and the perspective of the PL community. Okay, so core contribution. We need to formalize how inference algorithms interact with models and data. And the proposal in this paper is to extend probabilistic programming to have inference metaprogramming. This is the key point. In the paper, we've sort of shown that moves us from this sort of notion of probabilistic modeling with this black box solver to this programmable model. We've introduced new language constructs, and we've given it a first formalization of some of the key concepts that are associated with it. We have case studies that give a sense of performance benefits. And we have a prototype that's had some, I'd say, early research success in applications in data science, vision, and robotics. Although much more work remains to be done to really make this stuff practical that I hope this community will be able to help us with. Questions?
Maybe I'll start us off with a question. Really cool talk. You alluded to this, but I'm curious how your other paper in the session composes with what you just discussed. So does incremental inference work when you're doing this kind of metaprogramming?
Yeah, great question. So I guess there's at least two connections that are easy for me to describe in a couple sentences. So I'll leave it at that. The first one is that a common pattern in inference metaprogramming under this model is to set up some variables and add some data, do some inference, and then extend your probabilistic program to have more variables and more data. So that setting where you're interleaving, extending the model with doing inference, can be seen as a natural restricted case of incremental inference. Second, incremental inference could be used to generate better tactics. So it could be used as part of the backend in inference metaprogramming. So maybe really what I'm just trying to point at is this paper defines a framework which we think is pretty general coverage, but we certainly haven't covered the full range of operations that might be interesting, or all the programmability issues or verification and soundness issues associated with it. Great, thanks.
Hi. So I thought your talk really demonstrates to me that there's a wide variety of inference algorithms out there, and it made me really curious about why this huge diversity exists. So I guess my question is, what are the fundamental reasons I can't build one inference algorithm to rule them all?
Yeah, great. So that's a very deep question, and I would say that at one level, the only honest answer I can give, the most honest answer I can give, is that this is an opportunity for theorists. You know, what are the complexity classes of probably approximately correct probabilistic inference? And do they have the same structure we're familiar with from more traditional classes of problems? I mean, if they do, though, I think it's not surprising that there's a diversity of inference algorithms. And we're very familiar with the idea that, you know, although many problems with finite numbers of binary variables can be reduced to SAT, that's not how you build an email client. You know, by somehow setting up every sorting algorithm, and, you know, I mean, what I'm saying might even sound kind of crazy, right? It's like you would never use a SAT solver, or a typical programmer wouldn't try to use a SAT solver to solve every logic subproblem that arises in the course of ordinary programming, right? So I think that's one reason. Yeah, another frame is that for different applications and different model types, there are different characteristics of the posterior distribution that are functionally relevant. So on that first slide, where I showed this range of applications, right? In the case on the far left, you know, in statistics, we want, you know, very careful characterization of uncertainty that's kind of independent of the starting condition. In the machine learning application, we just want one pretty good setting of the parameters. And in the robotics application, we want to track small changes in uncertainty very quickly, but we don't need something that, you know, it's a key characteristic of the robot is that it knows where it was a few seconds ago. And so that kind of gives you a sense as why you might expect that good pragmatic approximation strategies will strike different trade-offs and use different primitives.